magnetic field on, then you can look at the, so this is the equation we're dealing with, okay? So let's come back. This is our mostly, I would say,
physics-based.
yeah, the physics-based.
This is a constitutive equation.
Yeah, the flow, the oscillation, and this is what we're dealing with. Everything just to move on from here, you can, mathematically there's no more challenge. You can just solve this equation and look at that. And the worst case is you fit it with experimental data. And the flow equation, you have this, that's the viscosity. And also you have the, where is that, electrical conductivity here. So you can measure both parameters at the same time. And the oscillation, some of the inertia, the spring constant, you can combine them, measure them through the measurement. Where is the force? I think I'm missing one. Oh yeah, the force term. The force term is on the surface, basically. The force connection between the two systems. One is liquid, one is solid, and the connection is on the surface. So actually this is a surface force, viscous force calculation. So combining two systems together. The rest is very simple, so it's just to solve these two equations simultaneously. You have the velocity field after you turn on the electric field at the time, how long does it take to reach steady state. And then you have the angle looking at this is initially it's 0, and then as you turn the rotating magnetic field, you have this process. So actually it's a transient process on average wise, and otherwise it's the system is keep rotating because the cup is pretty heavy. And then you turn it off, it goes back and then start rotating. It's also a transient process, but then start rotating again and then there's decay. So there are two processes. One is you turn it on. So during this time, the field is on, so you have a stirring force inside. And this time, there's nothing there, no field, it's just natural damping. So this is what we're dealing with, and we use this when there are only about probably 3 or 4 machines like this in the world. And of course the question is, how do I find fractional order calculus here? How do I use it here? And is there any way to do it? But that's one of the examples. And the rest is about, how do you calculate the velocity fields, looking at the velocity in the cup. This is the center. This is the tangential velocity. You see the moving boundary on the side of the cup. And then eventually, if you wait long enough, the stirring force is gone, so the velocity is basically totally by the side. This is the center of the cup, so the wall is moving back and forth, causing the flow velocity field to look like this. This is a calculation, and you can measure it based on the result, depending on the sensitivity we are looking at here, what kind of angle, what kind of frequency. So it's not that important here, but the previous discussion about the equations is the main part. This is just revisit these models, how do you calculate that. So if I have to write these equations, so we are dealing with, as we talked about earlier, we have conduction equation, thermal conductivity, which can be a function of time. Can you see it over there? This is 1D space. Let me change. So T in this case is the, let's say, temperature is a function of x and time, space and time. This is the equation we are dealing with typically. It can be rectangular system, it can be cylindrical system, it can be spherical coordinate system. And it can be 1D, this case is 1D, or I can put 2D or 3D in there. So this is one type of equation we are dealing with. Another type is actually flow equation, the simplified Navier-Stokes equation. So you have a pressure term, pressure gradient, and the viscous term. Simplified. You can put both of the del x squared also here also. So you have viscosity, so it's a nonlinear. U and V are velocity to be found. So you have equations of both U and V. It can be 3D, it can be different coordinate systems. So these are the things our starting point. So this is the energy equation, heat transfer in conduction case. This is the fluid flow in lots of, in half of the mechanical engineering, basically, all the computational science and fluid flow. And you can take out this term, let's say, so it becomes kind of like an equation simplified, second order differential equation. These are the things we use a lot when we do that. I don't know how to incorporate, how to find how to use fractional order differential calculus. Anyway, so let me stop here, and these two can talk about their research. One is in...
I can actually answer your question.
Let's talk. Let's talk. Let me put this one. Do you have yours here?
Yeah.
Yeah.
Right there.
Zilong, you do first then. Let's do it here. Get out.
So what liquid do you put in?
Oh, it's...
Mercury?
Mercury is one of them, but mercury you don't need high temperature. We actually do a semiconductor. It's tellurium, yeah, and cadmium, zinc, cadmium, tellurium. So these are the compound semiconductor for NASA. Look at the long wavelength sensors. So they build typical sensors. You build on silicon wafers, and they build on different semiconductors for different wavelengths.
Okay. Good afternoon, everybody. My name is Long. I'm a PhD student in Mechanical and Aerospace Engineering of the Utah State University, and my advisor is Dr. Heng here. And my research is the photothermal methods to measure the thermal properties of materials. Here is the equation which my boss just showed everybody. It's the assumption like the K is independent of the temperature and position. We can make a simplification to put the K out of this part. And here, please let me do a simple introduction of the thermal properties. In this equation, the K is the thermal conductivity, and we have three very important thermal properties here. The other two are the thermal diffusivity and the thermal effusivity. And these three thermal properties have a relationship here. And actually, the thermal conductivity K is not easy to measure directly, and it's our final A. And the thermal diffusivity, we have many methods in the world, many researchers doing that thing. And so right now we are focusing on the thermal effusivity measurement. Oh, sorry. Here is the explanation of the photothermal. Photothermal is photo plus thermal, and photo means laser, and thermal means heat. So photothermal means we use the lasers as a heat source to measure the thermal properties. Why we use laser as a heat source? It's because of the laser has three very important advantages. The laser has high power, give us a wide temperature range, and the low divergency, give us a high accuracy. Like my boss just said the spatial accuracy is some microns. And the most important factor is the high speed of the laser. It's because of the heat dissipated when you want to measure the property. So you have to do the measurement very fast. If you don't do the measurement very fast, the experimental data will be wrong, very, very wrong from the real thing. And actually, there are many photothermal methods, at least some famous ones here. And what we want to use is a reflection of the laser, because the thermal reflection method. Compared to the other famous methods here, our method have this good thing is give us a high spatial resolution, and it's easy to adjust, and